In the vast cosmic arena, where hundreds of billions of galaxies each contain hundreds of billions of stars, where black holes devour matter and neutron stars spin at impossible speeds, where supernovae explode with the brightness of entire galaxies, there exists something so rare, so elusive, that we have found only one strong candidate in all our searching. Among all the celestial wonders catalogued by humanity, among all the exotic phenomena predicted by physics, there is one type of object that stands apart in its scarcity. We're talking about Thorne-Żytkow Objects, and the fact that we've potentially identified just a single example makes them arguably the rarest thing in the observable universe. Think about that for a moment. We've found thousands of exoplanets. We've detected dozens of stellar mass black holes. We've observed hundreds of neutron stars. We've even caught glimpses of phenomena that lasted mere seconds before vanishing forever. But Thorne-Żytkow Objects? Just one candidate. One possible example in a universe containing an estimated 2 trillion galaxies. This isn't just rare. This is a level of cosmic scarcity that challenges our understanding of what's possible in the universe. It raises profound questions about the nature of stellar evolution, the limits of astronomical observation, and whether what we're looking at is truly what we think it is. The story of Thorne-Żytkow Objects is a story about edges. The edges of theoretical physics, the edges of observational astronomy, and the edges of what the universe allows to exist. It's a story that begins with a wild idea, continues through decades of fruitless searching, and arrives at a single, ambiguous candidate that might or might not be what we hope it is. But more than anything, it's a story about how the universe can create things so strange, so improbable, that finding even one example represents a triumph of human curiosity and scientific persistence. To understand why these objects are so extraordinarily rare, we first need to understand what they actually are, and trust me, the reality is stranger than most science fiction. Imagine taking a neutron star, one of the densest objects in the universe, the compressed core of a dead massive star, and hiding it inside another star that's still alive and actively burning. Picture a cosmic Russian nesting doll, where the innermost doll is made of matter so dense that a single teaspoon would weigh as much as Mount Everest, surrounded by layers of normal stellar material that extend outward for hundreds of millions of kilometers. This is a Thorne-Żytkow object, and it defies almost everything we normally think about how stars work. The structure is genuinely bizarre. At the center, crushed into a sphere perhaps 20 kilometers across, sits a neutron star. This isn't some small thing floating in the middle of the star. It's a gravitational monster, a stellar corpse with more mass than our Sun, compressed into something the size of a city. Surrounding this neutron star core is an envelope of hydrogen, helium, and heavier elements, the body of a red giant or supergiant star. This outer envelope might extend for distances comparable to the orbit of Mars or even Jupiter if we placed it in our solar system. From the outside, it would look like a fairly normal, if large, red giant star. You could observe it with a telescope, and without detailed analysis, you'd never know that deep within its glowing layers, something impossible was hiding. The inner workings are even more remarkable. The neutron star at the center creates an environment unlike anything found in a normal star. In a typical star, nuclear fusion occurs in a core where temperatures and pressures are high enough to fuse lighter elements into heavier ones. The energy from this fusion radiates outward, creating the light and heat we observe. But in a Thorne-Żytkow object, the neutron star has essentially replaced the normal core. Material from the giant star envelope falls inward, pulled by the neutron star's immense gravity. When this material hits the neutron star surface, it doesn't gently accumulate. It slams down with such force that it triggers nuclear reactions completely different from those in normal stars. This creates a situation where the star is powered not by fusion in a normal core, but by accretion onto the neutron star, and by unusual nuclear processes occurring in the superheated material surrounding it. The neutron star acts like a furnace of impossible heat, and the reactions it drives create elements and isotopes in abundances that simply don't occur in regular stars. This chemical peculiarity is ultimately the key to identifying these objects, because from the outside, they hide their true nature well. They masquerade as ordinary red giants, their secret only revealed when we carefully analyze the light coming from their surfaces and detect chemical signatures that shouldn't be there. The story of how scientists even conceived of such objects begins in the 1970s with two brilliant physicists, Kip Thorne and Żytkow Thorne, who would later win a Nobel Prize for his work on gravitational waves and become known to popular audiences as a scientific consultant on the film Interstellar. Was already establishing himself as a creative thinker about extreme astrophysics. Żytkow brought expertise in stellar structure and evolution. Together, they asked a question that seemed almost absurdly hypothetical. What would happen if you put a neutron star inside another star? In 1977, they published their theoretical work describing these hybrid objects. This wasn't science fiction speculation, it was rigorous physics. They worked through the equations governing stellar structure, the thermodynamics of accretion, the nuclear reactions that would occur in such extreme conditions. What they found was that, surprisingly, such an object could theoretically be stable, at least for some period of time. The neutron star wouldn't immediately sink to the center and destroy everything, and the giant star envelope wouldn't immediately be blown away. Instead, you could have a quasi-stable configuration where this cosmic chimera could exist for potentially millions of years. Their work was groundbreaking because it opened up a new possibility in the already complex landscape of stellar evolution. Stars, we had learned, could end their lives in different ways, depending on their mass. Lower mass stars became white dwarfs. More massive stars exploded as supernovae, leaving behind neutron stars or black holes. Binary stars could interact in complex ways, transferring mass, merging, creating exotic outcomes. But Thorne and Żytkow showed that there might be another pathway, another possibility hiding in the equations, where stellar death and stellar life could coexist in the same object. The theoretical work raised an obvious question. How could such an object actually form? You can't just place a neutron star inside a star. There has to be a physical process that creates this configuration. The most promising scenario involves binary star systems, those cosmic pairs where two stars orbit each other, locked in a gravitational dance that can last billions of years. Imagine a binary system where one star is significantly more massive than the other. The more massive star evolves faster, exhausting its nuclear fuel first. It swells into a red giant, then eventually explodes as a supernova, leaving behind a neutron star. Now you have a system with a neutron star orbiting a normal star. As the companion star ages and begins its own expansion into a giant, something remarkable can happen. The expanding envelope of the giant star begins to engulf the neutron star. As the neutron star moves through the outer layers of its companion, it experiences drag, a kind of friction from the stellar material. This drag causes the neutron star's orbit to decay. It spirals inward, moving deeper and deeper into the giant star. Eventually, if conditions are just. Right, the neutron star reaches the core region and settles there. having journeyed from being an external companion to becoming an internal feature of the merged system. There's another possible formation pathway that's even more dramatic. Imagine a binary system where the two stars are already quite close, perhaps born that way, or having migrated closer through various interactions. If one star becomes a neutron star while they're still close, and if the orbital configuration is just right, the neutron star might not initially be engulfed, but might gradually spiral inward through gravitational wave radiation and tidal effects. This is a slower process, but could also result in the neutron star eventually becoming embedded within its companion. A third, more violent scenario involves a direct collision. In dense stellar environments like the cores of globular clusters, where stars are packed much more tightly than in typical galactic neighborhoods, a neutron star and a giant star might actually collide directly. The neutron star would punch into the giant star, its enormous density allowing it to penetrate deep into the stellar interior. If it doesn't have enough energy to escape out the other side, it could become trapped inside, settling down to create a Thorne-Żytkow object. Each of these formation pathways requires a delicate balance of conditions. The neutron star can't be moving too fast, or it will punch completely through the giant star and escape. The giant star can't be too massive, or its gravity might collapse the system into something else entirely. The orbital parameters have to be just right. The timing of stellar evolution. Stages must align. When you add up all these requirements, you start to understand why these objects should be phenomenally rare. The universe might create billions of neutron stars and trillions of red giants, but bringing them together in precisely the right configuration to create a stable Thorne-Żytkow object happens about as often as winning the cosmic lottery. To truly appreciate how strange these objects are, we need to understand what a neutron star actually is, because calling it dense doesn't begin to capture the reality. A neutron star is what remains when a massive star exhausts its nuclear fuel and the core collapses catastrophically. In a normal star, the outward pressure from nuclear fusion balances the inward pull of gravity. When fusion stops, that balance is destroyed, and gravity wins. The core collapses in a fraction of a second, and in that collapse, the very atoms themselves are crushed. Electrons are forced into protons, creating neutrons through a process called inverse beta decay. What you're left with is matter-in, a state that doesn't exist anywhere else in the universe except in neutron stars, and potentially in the cores of the most massive atomic nuclei. The density is almost incomprehensible. A typical neutron star might contain 1.4 times the mass of our Sun compressed into a sphere just 20 kilometers in diameter. To put this in perspective, if you could somehow transport a sugar cube-sized piece of neutron star material to Earth, it would weigh about as much as all of humanity combined. Roughly 500 million tons a teaspoon would weigh more than Mount Everest. This isn't just dense in the way lead is denser than water. This is matter compressed to the absolute limit of what physics allows before gravity would collapse it further into a black hole. The surface of a neutron star is a nightmare landscape where gravity is hundreds of billions of times stronger than on Earth. The magnetic fields surrounding many neutron stars are the strongest in the universe, trillions of times more powerful than the strongest magnets we can create in laboratories. Some neutron stars spin hundreds of times per second, their surfaces moving at significant fractions of the speed of light. And now, imagine taking this object, this crushed stellar corpse, this gravitational monster, and placing it at the heart of another star. The neutron star doesn't stop being a neutron star just because it's inside something else. It retains all its properties, all its gravitational strength, all its incredible density. Inside a Thorne-Żytkow object, this neutron star core dominates the physics of the entire system. Material from the giant star envelope is constantly falling toward it, accelerated by gravity to tremendous speeds. When this material reaches the neutron star surface, it hits with such energy that the impact is almost like a continuous, ongoing thermonuclear explosion. The temperatures and pressures at the neutron star surface and in the immediately surrounding layers are far higher than those found in the cores of normal stars. This creates an environment where nuclear reactions can occur that simply don't happen in regular stellar interiors. Meanwhile, surrounding this compact inferno is the extended envelope of the giant star, and this is what makes Thorne-Żytkow objects so difficult to identify. From the outside, this envelope looks remarkably normal. It has a radius that might be hundreds of times larger than our Sun. Its surface temperature would be relatively cool, perhaps 3,000 to 4,000 degrees Celsius, which in stellar terms makes it a red or orange color. It would shine with the luminosity typical of a red giant or supergiant. An astronomer, looking at the sky without detailed analysis, would simply see what appears to be an ordinary giant star, perhaps nothing special at all. The envelope extends outward in layers, each layer at a different temperature and density. Convection currents move through these layers, carrying heat from the interior to the surface. From the outside, everything appears normal. The star might pulsate gently, as many giant stars do. It might have a stellar wind blowing off its outer layers. It would exist in the same regions of space as other giant stars, perhaps in the same clusters or associations. There's no obvious visual signature, no flashing sign that says, "Something impossible is hiding inside me." This disguise is remarkably effective. For decades after Thorne and Żytkow proposed their theory, astronomers searched for these objects without success, largely because they were looking for needles in a haystack, where the needles looked almost exactly like hay. You could observe 1,000 giant stars, and if one of them was a Thorne-Żytkow object, it wouldn't obviously stand out. This is why the key to finding them lies not in how they look, but in their chemistry, in the detailed analysis of the light coming from their surfaces. The chemistry of a Thorne-Żytkow object is where the weird physics at its core leaves an observable fingerprint. In a normal giant star, the elements you observe in the spectrum reflect the star's history of fusion and mixing. You see hydrogen, helium, carbon, oxygen, and heavier elements in ratios that make sense based on stellar evolution theory. But in a Thorne-Żytkow object, the nuclear processes occurring near the neutron star core are different, and these processes create unusual abundances of certain elements. The extreme environment near the neutron star allows for what are called rapid neutron capture processes, or R-process nucleosynthesis. In normal stars, elements heavier than iron are created through slower neutron capture processes, or through supernova explosions. But the conditions near a neutron star inside a Thorne-Żytkow object are so extreme that neutrons can be captured by atomic nuclei very rapidly, building up heavy, neutron-rich isotopes. These isotopes can then decay or be further processed, creating unusual patterns of elemental abundances. Specifically, theoretical models predict that Thorne-Żytkow objects should show enhanced abundances of elements like molybdenum, rubidium, and lithium. Molybdenum is particularly interesting because it's not easily produced. In normal stellar processes, rubidium can be created in certain asymptotic giant branch stars, but in different ratios than predicted. 4. Thorne-Żytkow objects' lithium is normally destroyed in stellar interiors. so finding enhanced lithium in what appears to be a giant star is itself unusual. The combination of these chemical signatures creates a pattern that shouldn't exist in a normal star, but should exist if there's a neutron star lurking in the core. For decades after the 1977 theoretical paper, astronomers searched for these chemical signatures. They looked at giant stars in our galaxy and in nearby galaxies. They took spectra of stars that seemed like they might be candidates. They analyzed the light looking for those telltale abundances, and they found nothing. Year after year, survey after survey, the searches came up empty. Some scientists began to wonder if Thorne-Żytkow objects might be so rare that none existed in the observable regions of our cosmic neighborhood, or if they might be so short-lived that the chance of catching one was vanishingly small. The problem was compounded by the observational challenges. Taking a detailed spectrum of a star requires significant telescope time, and there are millions of giant stars to potentially examine. You can't just randomly observe stars hoping to get lucky. You need some way to narrow down the candidates. But what criteria do you use when the objects you're looking for look like ordinary giant stars? Some astronomers focused on stars with slightly unusual properties, perhaps stars that seemed a bit overluminous or had slightly odd colors. Others looked at stars in environments where binary interactions were more common, like globular clusters or the cores of dwarf galaxies. The breakthrough came in 2014, though even calling it a breakthrough requires some caveats, because the story is more ambiguous than a triumphant discovery. A team of astronomers led by Emily Levesque, who had been specifically searching for Thorne-Żytkow objects, identified a star called HV2 112 in the Small Magellanic Cloud as a strong candidate. The Small Magellanic Cloud is a dwarf galaxy orbiting our Milky Way, located about 200,000 light-years from Earth. It's visible from the southern hemisphere as a faint smudge in the sky, and it's been a valuable laboratory for astronomers because its stars are all approximately the same distance from us, making comparative studies easier. HV 2112 had been catalogued before, listed simply as a red supergiant star, one of many thousands in the Small Magellanic Cloud. But when Levesque and her team took a detailed spectrum using the Magellan telescope in Chile, they found something remarkable. The chemical abundances didn't match what you'd expect from a normal red supergiant. There were excesses of several elements, and the pattern of these excesses matched the theoretical predictions for a Thorne-Żytkow object. The chemical evidence was compelling. HV2 112 showed elevated levels of rubidium and molybdenum, along with enhanced lithium and calcium. The molybdenum enhancement was particularly striking, with abundances about 10 times higher than what you'd expect in a normal supergiant of similar properties. The rubidium levels were also significantly elevated. Lithium, which should have been destroyed in the stellar interior long ago, was present in amounts that didn't make sense for a conventional star. When the team compared these abundances to theoretical models of Thorne-Żytkow objects, they found a reasonably good match. This wasn't ironclad proof. Science rarely works that way, especially in observational astronomy where you can't run controlled experiments. But it was the best candidate anyone had ever found, and it checked multiple boxes. The overall properties of the star, its luminosity, its temperature, its size, were all consistent with what you'd expect from a Thorne-Żytkow object. The chemical abundances showed the predicted peculiarities. There was no obvious alternative explanation that could account for all the observed features. After decades of searching, astronomers finally had something concrete to point to and say, this might be one. But why only one? In a universe containing trillions upon trillions of stars, why have we found only a single strong candidate? the answer lies in the extraordinary specificity required for these objects to form and survive. Let's walk through just how many things have to go right. First, you need a binary star system, and not just any binary, but one where the stars are relatively close together and where at least one star is massive enough to become a neutron star. Already you've narrowed down the possibilities significantly because most stars aren't in close binary systems, and most stars aren't massive enough. Next, the massive star needs to evolve and explode as a supernova without disrupting the binary system too severely. Supernovae can give neutron stars a substantial kick, potentially ejecting them from the binary entirely. If the kick is too strong, the neutron star flies away and you never get a Thorne-Żytkow object. The supernova also removes a substantial amount of mass from the system, which affects the orbital dynamics. The binary has to survive this violent event intact, which doesn't always happen. Assuming the binary survives, you now need the companion star to evolve into a giant at the right time and in the right way. The neutron star needs to spiral into the giant star, which requires the orbital parameters to be in a specific range. If the neutron star is too far away, it never gets close enough. If it's too close initially, the system might have merged before the companion became a giant. The timing has to align across millions of years of stellar evolution, with each stage happening in the correct sequence. Even when a neutron star does enter a giant star, there's no guarantee the result will be a stable Thorne-Żytkow object. If the neutron star is moving too fast, it might pass completely through the giant star and emerge on the other side. If it sinks too quickly to the center, it might trigger instabilities that destroy the system. The giant star envelope needs to be structured in just the right way to accommodate the neutron star without catastrophic consequences. The mass ratio between the neutron star and the giant star matters. The composition of the giant star matters. Dozens of parameters need to fall within relatively narrow ranges. Then, there's the question of how long these objects survive. Some theoretical models suggest Thorne-Żytkow objects might be stable for millions of years, existing as a distinct phase in stellar evolution. Other models suggest they might be much more transient, lasting perhaps only tens or hundreds of thousands of years before the system evolves into something else. If the lifetime is short, that dramatically reduces the number that exist at any given time. You might have many forming over the history of the universe, but if each one only lasts briefly, the instantaneous population is tiny. Consider the overall statistics. In our galaxy, there are roughly 100 billion stars. Of those, perhaps 10% are in binary systems where both stars are close enough to interact. Of those binaries, only a small fraction will have a massive enough primary star to become a neutron star. Of those systems, only some will survive the supernova without disruption. Of the survivors, only a fraction will have the right orbital properties for the neutron star to spiral into the companion. And of those, only some will actually form stable Thorne-Żytkow objects, rather than merging into something else or catastrophically disrupting. When you multiply all these probabilities together, you might end up with predictions that there are only a handful of Thorne-Żytkow objects in an entire galaxy at any given time. If there are only a few per galaxy, and we're primarily searching in our galaxy and a few nearby dwarf galaxies, finding even one becomes a statistical achievement. It's possible that there are more out there, hidden among the millions of red giants we haven't examined in detail. But the observational challenge is immense. You need high-quality spectra to detect the chemical anomalies, which means bright enough targets and substantial telescope time. Most giant stars are too far away for detailed spectroscopic analysis with current instruments. We're limited to searching the closest regions of space, which contain only a tiny fraction of the universe's stars. This brings us to a crucial question about the lifetime and stability of these objects. How long does a Thorne-Żytkow object actually exist once it forms? This is one of the biggest uncertainties in the theory, and it dramatically affects how many we expect to find. If these objects are stable for millions of years, comparable to the lifetime of a red supergiant, then there should be a reasonable population at any given time. But if they're short-lived transients, existing for only a brief period before evolving into something else, then catching one becomes much harder. The physics governing the lifetime is complex and not fully understood. The neutron star at the center is accreting material from the giant star envelope. But this accretion might not be steady. There could be instabilities, periods of rapid accretion alternating with quieter periods. The energy being pumped into the system by the neutron star affects the structure and stability of the envelope. If too much energy is deposited, the envelope might become unbound and blow away, leaving behind just the neutron star, or perhaps causing the system to transition to something like a Thorne-Żytkow supernova, if such things exist. Some theoretical work suggests that Thorne-Żytkow objects might lose mass at a significant rate through stellar winds, especially if they're very luminous. Strong stellar winds could gradually erode the giant star envelope, reducing the lifetime of the object. Other research indicates that the chemical composition changes occurring in the envelope could affect its opacity and structure in ways that might destabilize the system over time. There's also the question of what happens when the neutron star accretes enough material to potentially change its own properties, perhaps pushing it toward the mass limit where it might collapse into a black hole. Different theoretical models give different answers, with predicted lifetimes ranging from as short as tens of thousands of years to as long as several million years. This uncertainty is problematic because it means we don't know how many Thorne-Żytkow objects should exist. If the lifetime is at the short end of these estimates, finding even one example represents extraordinary luck or suggests that formation rates are higher than we think. If lifetimes are longer, then maybe we should be finding more candidates, and the fact that we've only confirmed one suggests either that we're not looking hard enough, or that formation is even rarer than the most pessimistic models predict. It's worth noting that while HV2112 is the strongest candidate, the case isn't completely closed. Science demands skepticism, and several alternative explanations have been proposed for its unusual chemical abundances. Some researchers have suggested that HV2112 might simply be a very unusual red supergiant, perhaps one that has dredged up material from deep in its interior through convection, bringing processed material to the surface. The problem with this explanation is that the specific pattern of abundances doesn't quite match what you'd expect from standard dredge-up processes. Another alternative involves mass transfer in a binary system without requiring a neutron star to be inside the star. If HV2112 received material from a companion star that had undergone unusual nucleosynthesis, perhaps through some exotic process, it might have acquired its peculiar chemistry that way. The challenge here is identifying what process in the companion could create precisely the right elemental abundances and how that material could be transferred without leaving other obvious signatures. Some astronomers have proposed that HV2112 might have formed in an unusual environment, or from gas with a non-standard composition, perhaps affected by a nearby supernova or other event. This seems less likely given our understanding of stellar formation and galactic chemical evolution. but it can't be completely ruled out without more observations. The scientific process requires considering all reasonable alternatives before accepting the extraordinary explanation. There's also measurement uncertainty to consider. Determining precise elemental abundances from spectra is not trivial. It requires detailed modeling of the stellar atmosphere, assumptions about temperature and pressure structures, corrections for various physical effects. Different analysis methods can sometimes give somewhat different results. While the team that discovered HV2, 112's peculiarities used rigorous methods and their results have been examined by other researchers, there's always some room for debate about whether the abundance anomalies are as strong as they appear, or whether they could be artifacts of the analysis. What makes the situation more frustrating is that we can't easily test the Thorne-Żytkow object hypothesis through additional observations of HV2-112. We can't probe inside the star to see if there's really a neutron star there. We can't measure the mass of the central object directly. We're limited to observing the surface and inferring what might be underneath. Some have suggested looking for variability patterns that might distinguish a Thorne-Żytkow object from a normal supergiant, or searching for faint X-ray emission that might come from accretion onto the neutron star. But these observations are at the limits of current capabilities. The detection challenges extend beyond just analyzing individual stars. The fundamental problem is that we need to examine massive numbers of giant stars to have any hope of finding more Thorne-Żytkow objects. There are millions of red giants and supergiants in the observable universe, but we can only study a tiny fraction in detail. Large spectroscopic surveys have revolutionized astronomy by observing millions of stars. But even these surveys often don't have the spectral resolution or signal-to-noise needed to detect the subtle chemical signatures of Thorne-Żytkow objects. The needle-in-haystack problem is particularly acute because we're looking for subtle differences in chemical composition, not obvious visual features. It's not like searching for a bright supernova or a rapidly moving asteroid. You need high-quality spectra, careful analysis, and even then, you might argue for years about whether a particular star is really a Thorne-Żytkow object or just an unusual, normal star. The ambiguity surrounding even our best candidate illustrates how difficult confirmation is. Geographic and instrumentation limitations also play a role. HV2-112 is in the Small Magellanic Cloud, which is only visible from the southern hemisphere. Many of the world's largest telescopes are in the northern hemisphere. The Small Magellanic Cloud, while relatively nearby in cosmic terms, is still 200,000 light-years away, far enough that even its brightest stars are relatively faint and require large telescopes and long exposures to study in detail. Stars in more distant galaxies are even harder to examine, effectively limiting our search to our galaxy and a few close neighbors. To put the rarity of Thorne-Żytkow objects in perspective, it helps to compare them to other rare cosmic phenomena. Consider magnetars, neutron stars with magnetic fields thousands of times stronger than normal pulsars. These are considered among the most extreme objects in the universe, yet we've confirmed about 24 magnetars. That's more than 20 times as many confirmed examples as we have. Thorne-Żytkow objects and magnetars themselves are considered exceptionally rare. Or consider quark stars. Hypothetical objects that might exist if neutron stars are compressed enough to break down neutrons into their constituent quarks. These are entirely theoretical with no confirmed examples, but there are several candidates under investigation. The fact that we have multiple quark star candidates but only one solid Thorne-Żytkow object candidate tells you something about relative rarities. Even compared to some of the most exotic objects theoretical physics predicts, Thorne-Żytkow objects are in a category of their own. Black hole binary systems that emit gravitational waves, like those detected by LIGO and Virgo, are rare events. Yet we've now detected dozens of these mergers. Hypervelocity stars, objects moving so fast they're escaping the galaxy, are rare, but we've found hundreds. Fast radio bursts, mysterious millisecond duration radio pulses from distant galaxies, were once considered incredibly rare, but we've now detected thousands. In comparison, having just one strong candidate for an entire class of stellar objects is remarkable. Part of what makes Thorne-Żytkow objects uniquely rare is that they represent an intersection of rare events. Binary evolution is common enough, and neutron star formation happens regularly in cosmic terms. But bringing these together in precisely the right configuration is where the improbability compounds. It's like winning several lotteries simultaneously. Many cosmic phenomena are rare because they require extreme conditions, but Thorne-Żytkow objects are rare because they require a specific sequence of events, each with its own low probability, all aligning correctly. To understand what's happening inside one of these objects in more detail, we need to think about the physics of the accretion process and the nuclear reactions it drives material from the giant star envelope, driven by the neutron star's gravity, falls inward through the stellar interior. As it approaches the neutron star, this material accelerates to tremendous velocities. By the time it reaches the neutron star surface, it's moving at a significant fraction of the speed of light, carrying enormous kinetic energy. When this material impacts the neutron star surface, that kinetic energy is converted almost instantaneously into heat. The temperatures reached are billions of degrees, far hotter than the cores of even the most massive normal stars. At these temperatures, nuclear reactions proceed at rates that dwarf normal stellar fusion. Nuclei collide with enough energy to overcome much stronger barriers than in normal stars. This opens up reaction pathways that simply don't exist in conventional stellar interiors. The neutron star surface itself is a strange place where nuclear physics operates in regimes we can barely explore in laboratories. The surface gravity is so intense that the scale height of the atmosphere, if you can call it that, might be measured in centimeters or millimeters. Any irregularities on the surface would be flattened almost instantly. The material that accretes onto the surface is immediately compressed and heated to extreme states. Nuclear reactions can proceed through chains that involve highly unstable nuclei, isotopes that would decay in fractions of a second under normal conditions, but can participate in reactions when densities and temperatures are extreme enough. Some of the nuclear processes occurring might be similar to those in X-ray bursts, which happen when matter accretes onto neutron stars in other contexts, like in low-mass X-ray binary systems. But in a Thorne-Żytkow object, the geometry and conditions are different. The accretion is occurring deep inside a giant star, surrounded by layers of stellar material, rather than in the relative vacuum of space. This affects how energy and processed material are transported outward and how the nucleosynthesis products are mixed into the star. Above the neutron star surface, there's likely a layer of superheated plasma where temperatures might be tens of millions or hundreds of millions of degrees. This region is heated both by the energy released from accretion and by the thermal energy leaking from the neutron star itself. Nuclear reactions continue in this hot layer, with the intense radiation field affecting how nuclei interact. The conditions allow for both rapid proton capture and rapid neutron capture processes, creating a soup of nuclear transformations that produces unusual isotopic ratios. As processed material moves outward through convection or other mixing processes, It carries the signatures of these extreme nuclear reactions. The unusual abundances of elements like molybdenum, rubidium, and lithium arise. From these processes, molybdenum, for instance, can be produced through neutron capture onto lighter elements under the extreme neutron fluxes that exist near a neutron star. The specific isotopic ratios depend sensitively on the temperature, density, and neutron flux, which is why the predicted abundance patterns for Thorne-Żytkow objects are distinctive. The energy transport through the Thorne-Żytkow object is also unusual. In a normal giant star, energy generated in the core moves outward primarily through radiation in the inner regions and convection in the outer regions. In a Thorne-Żytkow object, the energy source is localized at the very center, almost point-like compared to the distributed fusion reactions in a normal core. This concentrated energy source drives strong convection that can extend deep into the star. Material circulates in large convective cells, bringing processed material from near the neutron star to the outer envelope and carrying fresh material downward. This convective mixing is crucial for the observability of Thorne-Żytkow objects. Without efficient mixing, the unusual nuclear products would remain buried deep in the star, never reaching the surface where we could detect them spectroscopically. The fact that we can potentially observe these chemical signatures in the spectra of candidates like HV2 112 tells us that the interior structure must allow for significant mixing. This is consistent with theoretical models that predict Thorne-Żytkow objects should have extensive convective envelopes, similar to but perhaps even more vigorous than those in normal red supergiants. The connection between Thorne-Żytkow objects and gravitational wave astronomy is fascinating and represents a relatively new angle for understanding these objects. Gravitational wave detectors like LIGO and Virgo have opened a new window on the universe, allowing us to observe stellar mergers and collisions that were previously entirely theoretical. We've now detected numerous black hole mergers and several neutron star mergers, observing the gravitational waves produced when these compact objects spiral together and collide. Thorne-Żytkow objects might represent a different outcome of stellar mergers, specifically mergers involving neutron stars and giant stars. While we haven't directly detected gravitational waves from such an event, and indeed such signals would be much weaker than black hole mergers and harder to detect. The physics of compact object mergers is fundamental to understanding how Thorne-Żytkow objects form. When a neutron star spirals into a giant star, it loses orbital energy and angular momentum. Some of this energy goes into heating the stellar envelope, but some is radiated away as gravitational waves. The gravitational wave signal would be much weaker than those from compact object mergers in vacuum because the process occurs over longer timescales and the gravitational wave emission is affected by the surrounding stellar material. The study of gravitational waves has taught us that stellar mergers are more common than we once thought. The rates of black hole mergers observed by LIGO suggest that compact object binaries are abundant in the universe, and that their orbital evolution often leads to mergers. This has implications for Thorne-Żytkow objects because it suggests that the environments and conditions needed for neutron stars to interact closely with companion stars are not as rare as we might have thought. If black hole mergers happen frequently enough to detect multiple events per year, then neutron stars interacting with giant companions might also occur more often than early estimates suggested, even if the specific conditions for forming stable Thorne-Żytkow objects remain stringent. Gravitational wave astronomy has also refined our understanding of how compact objects behave during mergers. we've learned about the equation of state of neutron star matter by observing how neutron stars deform and merge. We've learned about the kicks that compact objects receive during formation and how these affect binary evolution. We've learned about the electromagnetic counterparts to neutron star mergers, like kilonovae, which are powered by the radioactive decay of neutron-rich elements synthesized during the merger. All of this knowledge feeds back into our theoretical models of how Thorne-Żytkow objects might form and what signatures they might produce. There's even a speculative connection between Thorne-Żytkow objects and the R-process nucleosynthesis that produces many of the heaviest elements in the universe. Neutron star mergers are now known to be important sites for R-process nucleosynthesis, creating elements like gold, platinum, and uranium through rapid neutron capture. The extreme conditions near the neutron star core in a Thorne-Żytkow object might also allow for R-process nucleosynthesis, though in a different environment than a merger. If confirmed, Thorne-Żytkow objects might represent another channel for producing heavy elements, albeit a rare one. The chemical signatures we observe in candidates like HV2, 112 could be telling us about nucleosynthesis. Processes that bridge the gap between normal stellar fusion and the extreme conditions of compact object mergers. Looking forward, the prospects for finding more Thorne-Żytkow objects depend critically on next-generation instruments and survey strategies. Several upcoming astronomical facilities offer hope for advancing this field. The Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, will survey the entire visible sky every few nights, cataloguing billions of stars. While its primary focus is on time-domain astronomy, finding things that change or move, the massive database it creates will be invaluable for identifying unusual stars that warrant follow-up spectroscopy. Large spectroscopic surveys are perhaps the most promising avenue. Projects like the SDSSV survey, the DESI survey, and future multi-object spectrographs on extremely large telescopes will observe millions of stars, obtaining spectra that can be searched for unusual chemical abundances. Machine learning algorithms can be trained to identify spectral patterns consistent with Thorne-Żytkow objects, automatically flagging candidates for detailed study. This approach turns the needle-in-haystack problem into a big data problem, using computational power to sift through vast amounts of information looking for rare signatures. The next generation of extremely large telescopes, the 30-meter telescope, the Giant Magellan Telescope, and the Extremely Large Telescope, will have the sensitivity to study individual stars in more distant galaxies and to obtain higher quality spectra of stars in nearby galaxies. This expands the volume of space we can search and increases the sample size of giant stars we can examine. With telescopes that have collecting areas several times larger than current facilities, we can study fainter stars and obtain better signal-to-noise on spectra, improving our ability to detect subtle chemical anomalies. Space-based missions also offer potential. The James Webb Space Telescope, while primarily focused on distant galaxies and exoplanet atmospheres, has capabilities that could be used to study nearby stars in unprecedented detail. Its infrared sensitivity is particularly useful for studying cool giant stars, which emit much of their light in the infrared. Future space telescopes with high-resolution spectrographs might be able to detect chemical signatures that are difficult to observe from the ground due to atmospheric absorption. Advanced data analysis techniques will be crucial. Modern machine learning algorithms can be trained on theoretical models of Thorne-Żytkow object spectra and then applied to survey data to identify candidates. Neural networks can learn to recognize complex patterns in spectra that might be too subtle for traditional analysis methods. These algorithms can process millions of spectra much faster than humans, dramatically increasing the rate at which we can search for rare objects. The challenge is ensuring that the algorithms are trained properly and don't miss candidates or produce too many false positives. There's also potential in multi-wavelength observations. While optical spectroscopy has been the primary search method, Thorne-Żytkow objects might have signatures in other parts of the electromagnetic spectrum. X-ray observations might detect emission from the hot accretion region near the neutron star. Though this signal would be heavily absorbed by the overlying stellar material and might be too faint to detect with current instruments, radio observations might reveal unusual emission mechanisms. Infrared observations can penetrate dust and probe the cool outer layers of giant stars. By combining observations across the electromagnetic spectrum, we might find diagnostics that help distinguish Thorne-Żytkow objects from normal stars. Theoretical work continues to refine predictions for what we should observe. Better models of the stellar structure, improved nuclear reaction networks, and more sophisticated simulations of convection and mixing all help sharpen the theoretical predictions for the chemical signatures. As our models improve, we can make more precise predictions for which elements should be enhanced and by how much, helping us design more targeted searches and interpret observations more accurately. Some researchers are also exploring what other observable properties might distinguish Thorne-Żytkow objects, such as specific variability patterns, unusual stellar winds, or subtle differences in their evolutionary tracks compared to normal giants. The implications of confirming Thorne-Żytkow objects extend deep into our understanding of stellar evolution. Stars are not static objects, but evolve through various stages over millions or billions of years. We've mapped out the main sequence of stellar evolution, understanding how stars of different masses live and die. But there are still exotic pathways and unusual outcomes that we're discovering or predicting. Thorne-Żytkow objects represent one. Such exotic pathway, a branch in the evolutionary tree that's rarely taken, but is possible under the right circumstances. If these objects exist and we can study them in detail, they would provide a laboratory for extreme physics that we can't replicate on Earth or study easily in other contexts. The nuclear reactions occurring near the neutron star core proceed under conditions intermediate between normal stellar interiors and the even more extreme environments of supernova explosions or neutron star mergers. Understanding these reactions could improve our knowledge of nuclear physics, particularly the properties of neutron-rich nuclei that are difficult to study in laboratories because they're unstable and decay quickly. Thorne-Żytkow objects also inform our understanding of binary star evolution, which is crucial for many areas of astrophysics. Most stars are in binary or multiple star systems, and the interactions between companion stars drive much of the diversity we observe in stellar populations. Mass transfer, tidal effects, common envelope evolution, and mergers all play roles in how binary systems evolve. Thorne-Żytkow objects represent an extreme case of binary interaction, and understanding them helps us understand the broader landscape of what's possible when stars interact. There are also implications for understanding stellar populations in galaxies. The chemical elements synthesized in stars and released into the interstellar medium through stellar winds and supernovae determine the composition of future generations of stars. If Thorne-Żytkow objects contribute to nucleosynthesis, even rarely, They might affect galactic chemical evolution in subtle ways. Elements that are primarily produced in Thorne-Żytkow objects might have distinctive abundance patterns in certain stellar populations, providing clues about the history of star formation and evolution in a galaxy. The question of what happens at the end of a Thorne-Żytkow object's life is still open. Several possibilities exist depending on the specifics of the system. If the giant star envelope is gradually lost through stellar winds, you might be left with an exposed neutron star that would then evolve as a normal isolated neutron star. If the neutron star accretes enough mass, it might exceed the maximum mass. A neutron star can support and collapse to form a black hole, possibly producing some kind of transient event. If instabilities develop in the system, it might disrupt catastrophically, perhaps producing an unusual type of supernova or other explosive event. Some theoretical work suggests that Thorne-Żytkow objects might end their lives as peculiar supernovae with distinctive properties. The presence of a neutron star at the center could affect how the final collapse proceeds if the envelope eventually becomes unstable and collapses. You might get a supernova powered by different mechanisms than normal core collapse supernovae, with unusual chemical abundances in the ejected material. Alternatively, the system might transition to a different configuration, perhaps becoming something like a high-mass X-ray binary if enough of the envelope is lost to expose the neutron star while material is still being accreted. The fact that we haven't observed such ending scenarios provides its own constraints. If Thorne-Żytkow objects commonly ended in distinctive explosive events, we might have observed such events even if we haven't identified the progenitors. The absence of obviously identified Thorne-Żytkow supernova or similar transients suggests either that these objects end their lives in more mundane ways, that don't produce distinctive signatures, or that they're so rare that even their death events are rarely observed, or that the ending events are sufficiently similar to other types of transients that we haven't recognized them as special. The story of Thorne-Żytkow objects also highlights the challenges and limitations of observational astronomy. We're limited by distance, by the faintness of objects, by the resolution of our instruments, by the amount of telescope time available. We can develop beautiful theories that predict exotic phenomena, but testing those theories requires finding the objects, which can take decades or longer. Even when we find candidates, we often can't prove definitively that they are what we think they are. We're forced to build cases based on indirect evidence, comparing observations to models, ruling out alternatives, but rarely achieving absolute certainty. This ambiguity is perhaps most evident in the continuing debate over HV2 112. Is it really a Thorne-Żytkow object? Or is there some other explanation for its unusual chemistry? We may not know for certain until we find more candidates or develop new observational techniques that can probe the interior structure of stars. The single candidate situation is scientifically frustrating because we can't compare multiple examples to see what properties they have in common and what varies. One example could be an anomaly, a statistical fluke, or a measurement error. Multiple examples would be much more convincing and would allow us to study the class of objects as a whole. There's something profound about the idea that an entire class of cosmic object might be represented by just one or two examples in the observable universe. It challenges our intuition about nature. We're used to things existing in large numbers, billions of galaxies, trillions of stars, countless planets. When we discover a new type of object, we usually find that it's actually common and we just hadn't noticed it before. Pulsars, quasars, gamma-ray bursts, exoplanets, all initially discovered as rare curiosities, all turned out to exist in large numbers once we knew how to look for them. But Thorne-Żytkow objects seem to be genuinely rare, not just observationally rare, but physically rare. The universe, for all its vastness, apparently doesn't make many of these hybrid stars. This rarity tells us something important about the constraints on stellar evolution and the specific conditions required for different outcomes. Not everything that's theoretically possible is common. Some pathways are taken so rarely that finding even one example is remarkable. This rarity also raises philosophical questions about the nature of scientific investigation. How do we study phenomena that occur only once or a handful of times? The scientific method relies on repeatability and statistics. We test hypotheses by making predictions and seeing if they're confirmed by observations. But when you have only one example, the statistics are poor. You can't distinguish between a genuine pattern and a coincidence. This is a challenge that astronomers face in studying many rare cosmic events, from supernovae in our galaxy to the most distant galaxies in the universe. Each object is unique in some sense, and we have to be careful about drawing general conclusions from limited samples. The search for Thorne-Żytkow objects also exemplifies the value of theoretical astrophysics. Kip Thorne and Anna Żytkow didn't observe these objects and then develop a theory to explain them. They worked from first principles, using the equations of stellar structure and physics to predict that such objects could exist. For nearly 40 years, their prediction had no observational confirmation. A more cynical view might have dismissed the theory as interesting but irrelevant if these objects don't actually exist. But the theoretical work was rigorous, based on solid physics, and it made specific predictions that could be tested. The discovery of HV2 112 vindicated that theoretical effort and showed the value of exploring what's possible, even if it seems improbable. This interplay between theory and observation drives much of astrophysics. Theorists imagine possibilities, constrained by the laws of physics, but often quite creative in exploring exotic scenarios. Observers then search for evidence of these predicted phenomena. Sometimes the observations come first. Pulsars were discovered before anyone really understood what they were. But often, theory leads the way. The universe is more complex and diverse than any human could imagine without the guidance of mathematical physics. And following the equations can lead to predictions of phenomena that seem absurd until we actually find them. In thinking about cosmic rarity, it's worth considering what else might be out there, even rarer than Thorne-Żytkow objects. Physics allows for many exotic possibilities. Quark stars, if they exist, might be rarer still. Strange matter stars, hypothetical objects made of strange quark matter, could exist, but might be even harder to identify. Primordial black holes from the early universe, if they exist, might be scattered throughout the cosmos in numbers we can only guess at. Boson stars, gravitational vacuum stars, and other speculative objects populate the theoretical literature. Their existence allowed by physics, but unconfirmed by observation. The universe might contain singular objects, things that exist only once in the entire observable universe. We tend to think in terms of populations and classes, but perhaps some phenomena are so specific, require such a precise alignment of conditions, that they occur only once across billions of years and trillions of galaxies. How would we even know if we found such a thing? How would we recognize it as a member of a class with only one example? This is perhaps the ultimate challenge in cosmic rarity. Objects so rare that we might not even recognize their significance if we observed them. Thorne-Żytkow. Objects remind us that the universe still holds mysteries, still has room for the unexpected. Despite centuries of astronomical observation, despite space telescopes, and gravitational wave detectors and sophisticated theories. There are entire classes of objects we've barely begun to study. Every answered question opens new questions. Every discovery reveals more unknowns. The landscape of possible phenomena is vast, and we've explored only a tiny fraction of it. There's something humbling about confronting cosmic rarity. We tend to think we have a good understanding of the universe, that we've catalogued its major components and understand its basic workings. And in some sense, we have. We understand how stars work, how galaxies evolve, how the universe expands. But the details, the edge cases, the rare phenomena that occur in extreme conditions or through unlikely sequences of events, these remind us how much we still don't know. A universe that contains objects as strange as Thorne-Żytkow objects is a universe that still has the power to surprise us. The human element in this story is also worth reflecting on. For decades, astronomers searched for these objects based largely on a theoretical paper. They devoted telescope time, wrote proposals, analyzed data, all in pursuit of something that might not exist. Emily Levesque and her team, when they identified HV 2112, were vindicated for their persistence, but they're also careful in their claims, recognizing the limitations of the evidence. This is science at its best, bold in imagination, rigorous in method, cautious in conclusions. The willingness to search for rare phenomena, even when success is uncertain, is what drives discovery. Looking at HV 112, that star 200,000 light-years away in the Small Magellanic Cloud, we're looking at light that left that star 200,000 years ago. If it really is a Thorne-Żytkow object, then hidden within that light are photons that originated from nuclear reactions occurring near a neutron star embedded in a giant star. Some of those photons were created by the decay of exotic nuclei, synthesized in conditions that don't exist anywhere else in the local universe. That light traveled through space for longer than modern humans have existed, crossing the intergalactic void to eventually strike a telescope mirror on Earth and reveal, encoded in its spectrum, hints of something almost unbelievably strange. The fact that we can deduce the existence of a neutron star inside another star by analyzing starlight is itself remarkable. We can't see the neutron star directly. We can't probe the interior of the star. We certainly can't travel there to investigate. All we have is light, and yet, from the precise wavelengths present and absent in that light, from the detailed patterns of absorption lines in the spectrum, we can infer chemical abundances. From those abundances, we can work backward to the nuclear reactions that must have produced them. From those reactions, we can infer the extreme conditions required. And from those conditions, we can conclude that something extraordinary might be lurking in the star's core. This is the power and the limitation of astronomy. We can reach across the universe with our observations, studying objects so distant that their light has traveled for millions or billions of years to reach us. But we're limited to passive observation. We can't experiment on stars. We can't adjust conditions and see what happens. We can only watch and measure and interpret. When studying rare objects, this limitation becomes acute. We have to extract every possible piece of information from the observations we can make, squeezing insights from data that's often noisy and incomplete. The continuing search for more Thorne-Żytkow objects is as much a technological challenge as a scientific one. We need bigger telescopes to study more stars and fainter targets. We need better spectrographs to capture the chemical signatures with higher precision. We need faster computers to process the vast amounts of data from surveys. we need more sophisticated analysis techniques to identify rare objects among millions of ordinary ones. Each advance in technology opens new possibilities for discovery, expanding the census of known objects and potentially revealing more examples of these elusive hybrid stars. But technology alone isn't enough. We also need ideas, theoretical frameworks that tell us what to look for and where. We need serendipity, the luck to point a telescope at the right star at the right time. We need persistence, the willingness to search even when previous attempts have failed. And we need a community of scientists willing to collaborate, share data, debate interpretations, and build on each other's work. The search for Thorne-Żytkow objects involves researchers across continents and institutions, each contributing pieces to the puzzle. If we do find more confirmed Thorne-Żytkow objects, what would that mean? First, it would validate the theoretical framework more strongly than a single ambiguous candidate can. Multiple examples would allow us to study the population, looking for patterns in their properties. Are they all similar, or is there a range of masses, luminosities, and chemical compositions? Are they found preferentially in certain environments, like dense star clusters or metal-poor dwarf galaxies? How do their properties correlate with each other? With multiple examples, we could test theoretical predictions more rigorously. We could see if the chemical abundances match the models, if the lifetimes are consistent with population statistics, if the formation scenarios we've proposed actually produce objects with the observed properties. We might discover that our models are wrong or incomplete, that Thorne-Żytkow objects have features we didn't predict. This is how science advances: predictions, observations, refinements, new predictions. Finding more examples would also allow us to study these objects as a class, rather than as individuals. We could ask statistical questions. How common are they really? How does their frequency depend on stellar environment or galactic properties? Are they more common in galaxies with certain star formation histories? Do they occur more often in binary-rich environments? These questions can only be answered with reasonable sample sizes, and one example provides almost no statistical power. There's also the possibility that we might find Thorne-Żytkow objects at different evolutionary stages. HV2112, if it is a Thorne-Żytkow object, represents a snapshot at one moment in its life. But these objects must evolve, changing in properties as they age. Finding objects at different stages would be like seeing different frames from a movie, allowing us to piece together the full life cycle. A young Thorne-Żytkow object might look different from an old one. One that's just formed might still be settling into equilibrium, while one, near the end of its life, might show signs of instability or mass loss. The possibility remains, of course, that HV2112 is the only one we'll ever find, or that it's not actually a Thorne-Żytkow object at all. Science must remain open to the possibility that our interpretations are wrong. Perhaps there's an alternative explanation for HV2112's chemical peculiarities that we haven't thought of yet. Perhaps Thorne-Żytkow. Objects are so rare that even in a universe with trillions of galaxies, only a handful exist at any given time. And we've happened to find the one in our cosmic neighborhood. Or perhaps they're so short-lived that catching one is extraordinarily lucky. And most of the time when we look, we miss the brief window when they exist. This uncertainty is part of what makes the story compelling. We're at the frontier of knowledge, dealing with a phenomenon at the edge of observability. The answers aren't clear. The evidence is suggestive, but not definitive. We're still in the discovery phase, still trying to understand whether this class of objects really exists, and if so, what their properties are. This is science in action, messy and uncertain, but driven by curiosity about the universe's most extreme possibilities. Reflecting on the journey from Thorne-Żytkow's original paper in 1977 to the identification of HV2 112 in 2014, it's striking how long the arc of discovery can be in astronomy. 37 years from theoretical prediction to first candidate. Generations of astronomers contributed to the search. Graduate students wrote theses searching for these objects. Postdocs developed analysis techniques. Senior scientists designed surveys and built instruments. Some of these people retired or moved to other research areas without ever seeing a candidate confirmed. This long-term commitment to answering fundamental questions about the universe is one of the noble aspects of scientific research. The story also illustrates how important it is to pursue difficult observations. There's always a tension in astronomy between studying things we can observe relatively easily and pushing the limits to study rare or faint phenomena. Telescope time is precious, and there's pressure to use it efficiently, to study objects where you're guaranteed interesting results. Searching for rare phenomena risks spending time and resources without finding anything. But without taking those risks, without pursuing difficult observations, we'd never discover the universe's true diversity. Someone has to look for the long shots, the improbable objects, the edge cases. Otherwise, we'd only know about the common phenomena, and we'd miss the weird and wonderful things hiding in the data. Thorne-Żytkow. Objects also represent a kind of cosmic beauty. Not visual beauty, since they look like ordinary red giants, but conceptual beauty. The idea of a star within a star, a neutron star core hidden inside a giant star envelope, has an elegance to it. It's unexpected, but makes sense once you understand the physics. It's the kind of idea that makes you think, of course that could happen, while simultaneously thinking, how is that even possible? The universe creating these hybrid objects through the complex dance of binary evolution and stellar mergers shows that reality is more creative than we often give it credit for. There's also something poetic about the scale contrasts involved. A neutron star 20 kilometers across, containing more mass than the Sun, sitting at the center of a star that extends for hundreds of millions of kilometers. The density contrast is equally extreme. The neutron star might have a density of several times 10 to the 14th grams per cubic centimeter, while the outer envelope has densities a trillion times lower. The temperature contrast is vast, billions of degrees near the neutron star surface, thousands of degrees in the outer envelope. This is a system of extremes, pushing the boundaries of what stellar physics allows. As we look toward the future, the search for Thorne-Żytkow objects will continue. New surveys will catalogue more stars. New instruments will enable more detailed spectroscopy. New theoretical work will refine predictions and suggest new search strategies. Perhaps within the next decade or two, we'll find more candidates. Perhaps we'll develop new observational techniques that can more definitively confirm whether a star has a neutron star core. Perhaps gravitational wave detectors will become sensitive enough to detect the formation of these objects in real time, as neutron stars spiral into giant companions. Or perhaps Thorne-Żytkow objects will remain elusive, the universe's rarest stellar phenomenon, represented only by that single ambiguous candidate in the Small Magellanic Cloud. If so, they'll stand as a reminder that the universe doesn't owe us easy answers, that some phenomena are so rare that even our best efforts might only catch glimpses of them. But even this outcome would be scientifically valuable, teaching us about the limits of what stellar evolution can produce and how improbable certain pathways really are. In the grand scheme of cosmic phenomena, Thorne-Żytkow objects occupy a unique niche. They're not the most energetic objects. That distinction belongs to things like gamma-ray bursts or quasars. They're not the densest. Black holes have them beat. They're not the largest. That would be giant molecular clouds or galaxy superclusters. What makes them special is their rarity, their hybrid nature, the way they embody a cosmic improbability that the universe somehow managed to create despite the odds. Standing back and considering the full picture, we're left with a sense of wonder and mystery. Somewhere out there in the universe, perhaps in our galaxy or in nearby galaxies, there might be a handful of stars that look ordinary from the outside, but hide extraordinary secrets in their cores. These stars, if they exist, are living out complex lives driven by physics at the extremes of what's possible. They're synthesizing elements through nuclear processes that occur nowhere else. They're powered by mechanisms that blend the normal and the exotic. And they're so rare that we may have found only one, or perhaps we haven't found any real ones yet. And HV2 112 is something else entirely. This uncertainty, this ongoing mystery, is fundamentally what drives science forward. We observe the universe, we build theories, we make predictions, we search for confirmation. Sometimes we find what we're looking for, sometimes we find something unexpected, and sometimes we find nothing and have to rethink our assumptions. The search for Thorne-Żytkow Objects embodies all of these aspects of scientific investigation. We have a prediction based on solid physics. We have a candidate that might confirm the prediction. But we don't have certainty, and we don't have a population of objects to study. Perhaps the most important message from the story of Thorne-Żytkow objects is that the universe still holds surprises. After centuries of astronomy, after sending probes throughout the solar system, after detecting gravitational waves and photographing black holes and finding thousands of exoplanets, there are still entire classes of objects that exist in theory but remain barely confirmed in practice. There are still phenomena so rare that finding even one example is headline news. There are still edges of the map where "Here be dragons" is written, where our knowledge fades into speculation and our observations hint at but don't fully reveal what's really there. Looking up at the night sky, knowing that among all those stars there might be only one or two that are Thorne-Żytkow objects, that among trillions of stars we've found only one strong candidate, gives perspective on cosmic rarity. It reminds us that the universe operates on scales of size, of time, of probability that dwarf human experience. Events that happen only once per galaxy, per million years, are rare beyond our intuition, yet they happen. Objects that require the alignment of multiple improbable circumstances exist, though in tiny numbers, and our ability to find even a single example of such phenomena speaks to both human persistence and the power of science to reveal hidden aspects of reality. So we return to where we began, to that fundamental observation that in a universe containing hundreds of billions of galaxies, each with hundreds of billions of stars, we have found only one strong candidate for one of the rarest cosmic objects ever theorized, HV. 2112 sits in the Small Magellanic Cloud, perhaps containing within its glowing envelope a neutron star core. Perhaps not. It stands as either a triumph of theoretical prediction and observational persistence, or as a cautionary tale about the difficulty of confirming exotic phenomena. Either way, it represents something profound about the nature of scientific exploration and the character of the universe itself. The story of Thorne-Żytkow Objects is still being written, each observation adding a sentence, each theoretical advance adding a paragraph. And somewhere among the stars, reality continues to exist, whether we observe it or not, hiding its secrets and occasionally revealing them to those patient and persistent enough to search. The search for Thorne-Żytkow objects also intersects with broader questions about the nature of scientific discovery and how we come to understand rare phenomena. Throughout the history of astronomy, there have been cases where theoretical predictions preceded observations by decades or even centuries. Neptune was predicted mathematically before it was observed telescopically. Black holes were theoretical constructs for half a century before we had strong observational evidence for their existence. Gravitational waves were predicted by Einstein in 1915, but not directly detected until 2015, a full century later. Thorne-Żytkow objects fit into this tradition of theory-leading observation, but with the added challenge that even now, decades after the prediction, we remain uncertain about whether we've truly found one. This uncertainty reflects fundamental challenges in observational astronomy. Unlike laboratory sciences where you can control variables and repeat experiments, astronomy is purely observational. We can't create a Thorne-Żytkow object in a laboratory to study under controlled conditions. We can't manipulate stellar evolution to see what happens when we change parameters. We're entirely dependent on finding natural examples and interpreting their properties from light that has traveled across vast distances. This limitation means that confirming the existence of rare phenomena becomes extraordinarily difficult, especially when the objects in question don't have obvious distinguishing features. The methodology used to search for Thorne-Żytkow objects illustrates modern astronomical techniques. Spectroscopy, the analysis of light broken down into its component wavelengths, has been the primary tool. When we observe the spectrum of a star, we see dark lines at specific wavelengths where elements in the star's atmosphere have absorbed light. Each element produces a characteristic pattern of absorption lines, like a fingerprint. By measuring the strength of these lines, we can determine not just which elements are present, but in what quantities. This technique, developed in the 19th century and refined continuously since then, allows us to measure the chemical composition of objects trillions of miles away with remarkable precision. For Thorne-Żytkow objects, the challenge is that the chemical signatures are subtle. We're not looking for the presence or absence of elements, but for unusual ratios and abundances. An element like molybdenum might be present in both normal red supergiants and Thorne-Żytkow objects, but in different amounts. Detecting a factor of 10 enhancement requires high-quality spectra with good signal-to-noise ratios and careful calibration. You need to measure not just that molybdenum is present, but exactly how much, and then compare that to theoretical models of stellar atmospheres to determine if the abundance is unusual. This kind of analysis is technically demanding. Stellar spectra contain thousands of lines from dozens of elements. Disentangling the contributions of different elements, accounting for the effects of temperature and pressure in the stellar atmosphere, and determining accurate abundances requires sophisticated modeling. The process involves iterative refinement, where you assume a model of the stellar atmosphere, calculate what spectrum that model would produce, compare it to the observed spectrum, adjust the model, and repeat until you achieve a good match. The elemental abundances that give the best match are your final result, but they come with uncertainties that depend on the quality of your data and the accuracy of your models. When Emily Levesque's team analyzed HV2112, they had to work through all these steps carefully. They obtained high-quality spectra using one of the world's premier telescopes, the Magellan Telescope, at Las Campanas Observatory in Chile. They used advanced stellar atmosphere models to interpret the spectra. They compared their results to theoretical predictions for Thorne-Żytkow objects from the literature. They also compared HV2 112 to other red supergiants to ensure that its chemical peculiarities were truly anomalous and not just natural variations within the normal population. This careful, methodical approach is essential in modern astronomy, especially when claiming to have found something as rare and exotic as a Thorne-Żytkow object. The reaction of the astronomical community to the HV2 112 discovery was cautiously enthusiastic. The paper announcing the candidate was published in a respected journal and received significant attention. News articles appeared in popular media, explaining to the public that astronomers might have found one of the universe's rarest objects. But within the scientific community, the response was measured. This is exactly as it should be. Extraordinary claims require extraordinary evidence, and while the evidence for HV2 112 being a Thorne-Żytkow object was intriguing, it wasn't definitive. Other astronomers began planning follow-up observations, looking for additional candidates, and thinking about alternative explanations. This scientific back and forth is a healthy part of the process. Science advances not through single definitive observations, but through accumulation of evidence, debate, and refinement of ideas. When a surprising discovery is announced, the community scrutinizes it carefully. Are there systematic errors in the observations? Could the data be explained differently? Are the theoretical models being compared to observations really accurate? This skepticism isn't cynicism. It's the quality control mechanism that keeps science reliable. Ideas that can withstand this scrutiny become accepted. Those that can't are modified or discarded. In the years since the initial announcement about HV2 112, there has been additional work examining this star and searching for other candidates. Some follow-up observations have confirmed the unusual chemical abundances, strengthening the case. Other studies have examined large samples of red supergiants looking for similar patterns, with mixed results. A few additional candidates have been proposed, though none as compelling as HV2 112. The field remains active, with researchers continuing to refine theoretical models and search for more examples. This is how science works on problems at the frontier, not through single breakthroughs, but through sustained effort over years and decades. The broader context of binary star evolution is crucial for understanding Thorne-Żytkow objects. Binary stars are incredibly common in the universe, with recent surveys suggesting that the majority of stars form in binary or multiple systems. The interactions between stars in these systems drive much of the diversity we observe in stellar populations. Mass transfer, where one star pulls material from its companion, can create exotic objects like blue stragglers, Type Ia supernovae progenitors, and X-ray binaries. Common envelope evolution, where one star expands to engulf its companion, can dramatically shrink binary separations and lead to mergers. Understanding all these interaction channels is essential for understanding how stars evolve and how the universe's stellar population changes over time. Thorne-Żytkow objects represent one possible outcome of binary evolution, specifically the case where a compact object ends up inside a normal star. But there are related phenomena that are also rare, but perhaps slightly less exotic. For example, there are systems called symbiotic stars, where a white dwarf orbits within the extended envelope of a red giant. These systems show some similarities to Thorne-Żytkow objects, a compact object interacting with a giant star envelope. But the compact object is a white dwarf rather than a neutron star, and it typically orbits within the envelope, rather than settling at the center. Symbiotic stars are rare, but not as rare as Thorne-Żytkow objects, with hundreds known. The comparison helps illustrate why neutron star cores are so much more unusual. They require more extreme formation conditions. Another related phenomenon is that of planets or brown dwarfs that spiral into their host stars. This is thought to happen occasionally as planetary orbits decay through tidal interactions. When a planet or brown dwarf plunges into a star, it might temporarily affect the star's structure and observable properties. However, the mass ratio is very different from a Thorne-Żytkow object. A planet or brown dwarf has far less mass than a neutron star, so the effects are less dramatic. Still, these events show that having one object embedded inside another star is not entirely unprecedented. It's the specific case of a neutron star core that makes Thorne-Żytkow objects so special. The role of metallicity in Thorne-Żytkow object formation is an interesting consideration that researchers have explored. Metallicity, in astronomical terms, refers to the abundance of elements heavier than hydrogen and helium. Stars with different metallicities evolve somewhat differently. Their radii, lifetimes, and stellar wind strengths all depend on metallicity. This could affect the formation rate of Thorne-Żytkow objects because stellar radii determine whether binary systems will interact, and stellar winds affect mass loss rates and orbital evolution. Some theoretical work suggests that Thorne-Żytkow objects might form more readily in low metallicity environments, which could be one reason why HV2 112 is in the Small Magellanic Cloud, a galaxy with lower metallicity than the Milky Way. The Small Magellanic Cloud itself is an interesting laboratory for studying stellar populations. It's close enough that we can observe individual stars in detail, but it's a separate galaxy with its own star formation, history, and chemical composition. Astronomers have studied thousands of stars in the Small Magellanic Cloud, cataloguing everything from massive young stars to ancient low-mass stars. The fact that our best Thorne-Żytkow object candidate is in this galaxy rather than in the Milky Way might be telling us something about where these objects preferentially form, or it might just be a statistical accident. With only one candidate, it's impossible to say. The observational campaigns to search for Thorne-Żytkow objects have evolved over the years as technology has improved. Early searches in the 1980s and 90s were limited by detector technology and computing power. Spectrographs were less sensitive, requiring longer exposure times. Data analysis was more laborious, with spectra often analyzed by hand or with simple programs. As CCD detectors replaced photographic plates and as computers became more powerful, the efficiency of spectroscopic surveys increased dramatically. Modern searchers can obtain high-quality spectra of hundreds of stars per night and process the data using automated pipelines, vastly increasing the rate at which potential candidates can be screened. Machine learning and artificial intelligence are beginning to play a role in the search for rare objects like Thorne-Żytkow objects. Neural networks can be trained to recognize patterns in spectroscopic data that might indicate unusual chemical compositions. These algorithms can process enormous datasets, flagging interesting candidates for human follow-up. The advantage of machine learning is that it can find subtle patterns that might not be obvious to human analysts and can do so at a scale impossible for traditional methods. The challenge is ensuring that the algorithms are properly trained and validated, that they don't introduce biases, and that they don't miss genuinely unusual objects that don't fit the training data patterns. One particularly intriguing aspect of Thorne-Żytkow objects is what they might tell us about the final stages of massive star evolution. Massive stars, those with more than about 8 times the Sun's mass, end their lives in supernova explosions, leaving behind neutron stars or black holes. But the details of this process are still not fully understood. Exactly which stars become neutron stars versus black holes? What determines the properties of the remnant? How much mass is lost in the supernova explosion? These questions are active areas of research, and Thorne-Żytkow objects provide another angle for investigation. If we can determine how often they form and what happens to them, that constrains our models of massive star evolution and supernova physics. The connection to our process nucleosynthesis deserves more detailed exploration. The R process, or rapid neutron capture process, is responsible for creating about half of the elements heavier than iron, including elements like gold, platinum, europium, and many others. For decades, the primary site of R process nucleosynthesis was thought to be supernova explosions. However, recent work, particularly observations of neutron star mergers, has shown that these mergers are important R process sites and might even be the dominant source. Thorne-Żytkow objects represent a third potential site, though likely a minor one given their rarity. The nuclear physics of R process nucleosynthesis requires extreme conditions, high neutron densities, and short timescales. Near the neutron star core in a Thorne-Żytkow object, material is subjected to intense neutron fluxes from the neutron star itself and from neutron-producing reactions in the superheated accretion region. Atomic nuclei can rapidly capture multiple neutrons, building up to heavy, neutron-rich isotopes that would never form in normal stellar environments. These neutron-rich nuclei then decay through beta decay processes, producing the stable heavy elements we observe. The specific pattern of abundances depends on the temperature, density, and neutron flux, which is why theoretical models can make predictions about what chemical signatures to expect. If Thorne-Żytkow objects are confirmed and studied in detail, they could help us understand R process nucleosynthesis better. We could compare the elemental abundance patterns observed in these objects to theoretical predictions and to abundances observed in other R process sites like neutron star merger remnants. This comparison would help us understand which nuclear reactions are most important and how sensitive the process is to different conditions. Even though Thorne-Żytkow objects are rare, they might produce distinctive R process signatures that could be recognized in old stars that formed from gas enriched by earlier Thorne-Żytkow object winds. The question of whether Thorne-Żytkow objects could be detected through other means besides optical spectroscopy is worth considering. Could they emit X-rays detectable by space-based X-ray telescopes? The accretion of material onto the neutron star should release X-rays, as material heated to millions of degrees emits strongly in the X-ray band. However, these X-rays would have to travel through the entire envelope of the giant star to reach us, and they would be absorbed by the stellar material. Calculations suggest that any X-ray emission would be heavily attenuated, making detection extremely difficult with current instruments. Future X-ray telescopes with higher sensitivity might have a better chance, especially if pointed at known candidates like HV2 112. Could gravitational lensing help us detect Thorne-Żytkow objects? Gravitational lensing occurs when a massive object bends the path of light from background sources. While Thorne-Żytkow objects are certainly massive, they're not massive enough to produce strong lensing effects that would be easily detectable. Microlensing, where a star passing in front of a background star briefly brightens it through gravitational focusing, could in principle occur with a Thorne-Żytkow object as the lens. But the lensing signature wouldn't distinguish it from any other star of similar mass. so lensing is unlikely to be a useful detection method. Could neutrino observations help? Neutrinos are nearly massless particles that interact very weakly with matter. They're produced in nuclear reactions and can escape from dense environments where photons would be absorbed. The nuclear reactions occurring near the neutron star core in a Thorne-Żytkow object should produce neutrinos. However, even these reactions are probably not energetic enough to produce detectable neutrino fluxes at the distances of potential Thorne-Żytkow objects. Neutrino detectors like IceCube or Super Kamiokande are sensitive to very high energy neutrinos from sources like supernovae or active galactic nuclei. But the neutrino flux from a Thorne-Żytkow object thousands of light years away would be far too faint to detect with current technology. The most promising additional detection method might be monitoring for variability. If Thorne-Żytkow objects undergo periodic changes in brightness, temperature, or other observable properties, this variability could provide a diagnostic. Normal red supergiants often show irregular variability due to convection and pulsations. But Thorne-Żytkow objects might have distinctive variability patterns related to the accretion process or to instabilities in the envelope. Long-term photometric monitoring of candidates like HV2112, looking for periodic or quasi-periodic variations, could potentially reveal signatures that help confirm their nature. This is an area where modern time-domain astronomy, with surveys that repeatedly observe the same patches of sky, could contribute to Thorne-Żytkow object research. The theoretical modelling of Thorne-Żytkow objects has advanced considerably since the original Thorne and Żytkow paper. Modern stellar evolution codes can compute detailed models of these objects, tracking their structure from the neutron star core through the envelope to the surface. These models incorporate complex physics, including convection, nuclear reactions, energy transport, and mass loss. They can predict observable properties like surface temperature, luminosity, and chemical abundances, which can then be compared to observations. However, these models face challenges because some of the relevant physics is not fully understood. Convection in stellar envelopes, for example, is a turbulent fluid dynamics problem that we can't solve from first principles. Instead, we use approximate treatments that may not capture all the relevant effects. The uncertainties in the models mean that theoretical predictions come with error bars. When we say a Thorne-Żytkow object should have 10 times more molybdenum than a normal supergiant, that's a prediction with uncertainties that might be factors of 2 or 3. This uncertainty makes it harder to definitively confirm candidates because the observations have to be compared to predictions that themselves are uncertain. As stellar modeling improves, these uncertainties will shrink, but there will always be some level of model-dependent interpretation required. This is another reason why finding multiple candidates would be valuable. We could test whether they all show the predicted patterns despite model uncertainties. Another aspect worth considering is the public perception and communication of rare astronomical phenomena. When the HV2112 discovery was announced, it generated significant public interest. Articles appeared explaining Thorne-Żytkow objects to general audiences, often using analogies and comparisons to help people grasp the concepts. The idea of a star within a star captures the imagination, and the extreme physics involved, neutron star densities, exotic nuclear reactions, has inherent appeal. However, communicating the uncertainties is also important. Journalists and scientists have to balance making discoveries exciting and accessible while not overstating what's actually been confirmed. The Thorne-Żytkow object story exemplifies this balance. It's a potential discovery of something remarkable, but it's not yet definitive proof. The educational value of studying rare phenomena like Thorne-Żytkow objects extends beyond the specific scientific questions. These objects provide opportunities to teach about stellar evolution, nuclear physics, gravitational physics, and observational astronomy. Students learning about stars naturally want to know about the most extreme and unusual cases, not just the typical examples Thorne-Żytkow objects serve as a bridge between. Basic stellar astronomy and advanced topics in astrophysics. They show how theoretical physics can predict phenomena that are then searched for, observationally. They illustrate the challenges of confirming rare objects, and they demonstrate how science works at the frontier of knowledge, with uncertainties and debates that eventually lead to better understanding. Looking at the history of stellar astrophysics, we see a progression from simple models to increasingly sophisticated understanding. In the early 20th century, we didn't even know what powered stars. The discovery of nuclear fusion as the energy source was a major breakthrough. Understanding how stars of different masses evolve through various stages took decades of theoretical and observational work. Recognizing that binary interactions dramatically affect stellar evolution came later. We're still refining our understanding, with Thorne-Żytkow objects representing one of the exotic endpoints that theory predicts, but we're only beginning to observe. This progression reminds us that science is never finished. Each answered question leads to new questions. Each new class of objects discovered forces us to expand our theoretical frameworks. The universe is more complex than any theory can fully capture, and observations continually challenge and refine our models. Thorne-Żytkow objects, whether we've truly found one or not, are part of this ongoing exploration. They represent our attempt to understand what's possible in the universe, to map out all the different pathways stellar evolution can take, to see the full richness of cosmic phenomena. The technological requirements for advancing Thorne-Żytkow object research illustrate broader trends in astronomy. We need bigger telescopes because fainter objects can then be studied. The next generation of extremely large telescopes with mirror diameters of 25 to 40 meters will collect far more light than current facilities and will enable spectroscopy of stars in more distant galaxies. We need better detectors because higher sensitivity and lower noise allow for more precise measurements. Modern CCD and infrared array detectors are vastly superior to those available even 20 years ago. We need more powerful computers because processing the data from large surveys and running complex models requires substantial computational resources. Cloud computing and machine learning are changing what's computationally feasible. We also need better coordination and data sharing. Astronomy has become increasingly collaborative, with large surveys releasing their data publicly so that researchers worldwide can analyze it. Virtual observatories and online databases make it possible to access observations from multiple telescopes and wavelengths. This open science approach accelerates discovery because researchers don't have to repeat observations and can combine data in new ways. For Thorne-Żytkow object research, this means that spectroscopic surveys conducted for other purposes can be mined for candidates, and that follow-up observations can be planned more efficiently using existing data to prioritize targets. The interdisciplinary nature of modern astrophysics is evident in Thorne-Żytkow object research. Understanding these objects requires knowledge from multiple fields. Stellar structure and evolution theory provides the framework for understanding how stars behave. Nuclear physics tells us what reactions occur under extreme conditions. Hydrodynamics and fluid mechanics are needed to understand convection and mixing. Gravitational physics governs the binary interactions that lead to formation. Observational astronomy provides the techniques to find and study candidates. Computational science gives us the tools to model complex systems. No single researcher can be expert in all these areas, so collaboration across specialties is essential. This brings us to think about the future possibilities beyond just finding more Thorne-Żytkow objects. What else might we discover as our observational capabilities improve? Are there other hybrid objects we haven't imagined yet? Could there be black holes inside stars, similar to Thorne-Żytkow objects, but with an event horizon at the center instead of a neutron star? Theoretical work suggests such objects might be possible, but would be even more unstable and short-lived than Thorne-Żytkow objects. Could there be stars with unusual internal structures that we haven't predicted? The universe has surprised us before with phenomena like magnetars and soft gamma repeaters that weren't anticipated by theory. There's no reason to think we've exhausted the possibilities. The philosophical implications of cosmic rarity are worth pondering. Thorne-Żytkow objects, if they truly exist at the level of scarcity we observe, remind us that the universe can create things in ones and twos, not just in vast populations. This challenges our statistical intuitions. We think of scientific laws as describing regularities, things that happen predictably. But some phenomena are so contingent on specific circumstances that they're better described as cosmic accidents, allowed by physics but occurring only rarely. This doesn't make them less real or less interesting. If anything, it makes them more fascinating because they show us the boundaries of what's possible. There's also something profound about the act of searching for rare phenomena. It requires a certain kind of scientific courage, the willingness to pursue difficult questions, knowing that you might not find answers in your career. The astronomers who've spent years searching for Thorne-Żytkow objects knew the odds were against finding one. They pursued the search anyway because the question was important and the potential discovery significant. This is science at its best, driven by curiosity and the desire to understand, rather than by guarantees of success. It's a reminder that progress comes not just from answering easy questions, but from tackling hard ones. As we conclude this exploration of Thorne-Żytkow objects, we return to the central marvel. In all the vast universe, with its billions of galaxies and trillions of stars, we have found only one strong candidate for these hybrid objects. Whether HV2 112 truly harbors a neutron star in its core remains uncertain, but the search for these objects has already taught us much about stellar evolution, nuclear physics, and the limits of observation. The story continues, with each new observation potentially bringing us closer to confirmation or leading us to revise our understanding. And somewhere among the stars, whether common or breathtakingly rare, Thorne-Żytkow objects either exist or they don't, waiting for us to uncover their secrets through the patient application of science and the relentless human drive to understand the cosmos in all its strange and wonderful diversity. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.